Hey everybody! In this video, I will be determining how to find the empirical and molecular formulas of compounds. So first thing you got to know is the difference between empirical formulas and molecular formulas. So an empirical formula is the simplest formula for a compound. So it's like the most reduced version of it. It has the smallest possible whole number ratio of elements to each other. The molecular formula is the actual formula of the molecule. The empirical formula is just something we use in order to get the molecular formula. So a question might look something like this. I might give you a compound and say, all right, what is the empirical formula of this molecule? So say I were to give you C2H4. That's the actual molecular formula. If I were to ask you for the empirical formula, then we just simplify this, and that just means we reduce the subscripts. So if our formula is C2H4, 2 and 4 are both divisible by 2. So the most reduced version of this compound would be CH2, and that would be the empirical formula. Now that's the easy version that you could get. Now, the ones that you will most likely see, and in cases where we see the use of the word empirical formula, is when machines pop out percentages of elements within a molecule. So this is really something that a question would look like, or something that you could come across in the lab. So what is the empirical and molecular formula of a compound that is 60% carbon, 13.4% hydrogen, and 26.6% oxygen? It has a molecular mass of 180.28 grams per mole. So we have to take this in phases, and there are a lot of steps. So we want to first simplify it as much as possible, and because it spits out percents, we're going to assume for simplicity that we have 100 grams of the whole substance. So then what we can do is we can start by switching those percent signs to gram signs, and we're going to convert it to moles. So instead of 60% carbon, we're going to write 60 grams of carbon, and then we convert it to moles. And the molar mass of a carbon is 12.01, so that goes in the bottom. And that is equivalent to 1 mole. So we do this for each of the elements involved. Okay, so I've finished calculating, converting these atoms to moles. One thing that I will point out, you do not have to put a unit on the answer, because we do have more steps after this, and you do not count things as diatomic. So we actually just use their masses as seen right on the periodic table. All right, so to get the simplest whole number ratio after we convert these to moles, we want to get a whole number. So we have to divide everything by the smallest number. In this particular problem, the smallest number is 1.66. So I'm going to divide that out now. All right, so I have divided by the smallest number, and we get nearly whole numbers here. So much that 3.01 is so close to a whole number that we can say that it equals 3. 8.01 is so close that we can say it's a whole number of 8. That's a very messy 8. But 8 is so close to a whole number that we can say it is 8. And then the 1 is obviously a 1. So these numbers here become the subscripts for each of the elements that they come after. So the 3 would be a subscript for the carbon, the 8 would be a subscript for the hydrogen, and the 1 is a subscript for the oxygen in the empirical formula. So for this compound, the empirical formula would be C3H8O, and we don't have to put the 1. So again, where we are seeing that is we have C3H8O and there's one of them. So I just write that down and we call that the empirical formula. Now we can use this empirical formula to get our molecular formula. And how we do that is we have to use this piece of the question that talks about the molecular mass. And so it says that it has a molecular mass of 180.28. To get your empirical formula from the molecular formula, we want to see how much bigger this is from the empirical formula's mass. So what we need to do is we end up dividing the molecular mass by the empirical mass to see how much larger it is. Now this should come out to a whole number ratio, but the first thing you have to do is you have to actually calculate the mass of the empirical formula. So I'm going to do that now. All right, you can see here for the empirical mass, this is my math, and it came out to be 60.094. So that is the empirical mass. The molecular mass is given to us in the problem. So we just have to divide those two numbers. So we have 180.28, and we need to divide it by the empirical mass. And again, I'm getting that from this formula or this equation right here. And the empirical mass is 60.094. And we will get very close to a whole number, or at least you always should. Now, whatever we get here, it's saying that the molecule is this many times larger than the empirical formula. So when we divide 180.28 divided by 60.94, we get 2.99997, blah, blah, blah. So that is 3. What that means is that the molecular formula is 3 times bigger than the empirical formula that we found. So then our molecular formula, how we find it, is we just have to multiply all these subscripts within the empirical formula by 3, and that will give us the molecular formula. So for this particular compound, the molecular formula would end up being, for carbon, since in the empirical formula, carbon's subscript is 3, and if in the molecular formula, it is 3 times bigger. 3 times 3 is 9. So in the molecule, it'll be C9. For hydrogen, 8 in the empirical formula, but 8 times 3 is 24. And then finally, if we have oxygen, and there's only one present in the empirical formula, in the molecular formula, 1 times 3 would be O3. That is how you find your empirical and molecular formulas.